starts getting territorial and insisting, well, we're signing your paycheck, so you have to put our name first. This is, it's great to be here. I feel like I'm part of the transition on this third day from the GP summer school to the UQ workshop tomorrow. So Gaussian processes will feature sort of tangentially in what I say. But it's great to be here, and it's great to have the opportunity to speak, and thank you to the organisers for arranging that and laying it on. I'll talk about probabilistic numerics for differential equations. So this is something of a follow-up to what Mark talked about yesterday. And it is joint work with Mark Girolami and his graduate student John Cocaine at Warwick. But actually, this is really a combination of two talks. So on the PDE side, it's work with John and Mark and with Chris Oates at University of Technology Sydney, but soon to come back to the UK, to Newcastle. But on the ODE side, California. So what Mark talked about yesterday, I think I will probably try to spend more time. Okay. Is that better? Okay. In view of time, I'll give some introduction because I think probabilistic numerical ideas, I don't think they're alien to this community, but I think they bear some repetition because it's a noisy channel, and Shannon tells us that repetition on a noisy channel is a good thing if you want the recipient to understand what you're saying. I think I'll focus mostly on probabilistic numerics for ODEs, but if time permitting, I'll talk about probabilistic meshless methods for PDEs as well, and give some closing remarks. So, my spin on Mark's historical slide is what do we mean when we talk about probabilistic numerics? And I would say certainly if you reach back into history, and as someone said, predicting the past is a subtle thing. You can find sort of antecedents of probabilistic reasoning about deterministic problems reaching quite at least a century back in the mathematical literature. But I would trace its modern development to stuff around the end of the 80s and beginning of the 90s, where probability starts to get used to answer questions that really, on a mathematical level, have only one well-defined deterministic answer. So a good example being quadrature, that you want to, you're given, perhaps in closed form, some sines and cosines and exponentials, but an integrand that you want to integrate, let's say from 0 to 1. It's smooth enough that there's no ambiguity about whether this function is measurable or anything awful like that. The integrand has an integral, and you simply just don't have a primitive. You don't have an antiderivative for this, so the fundamental theorem of calculus is no help. So you're going to have to integrate this function numerically. That's the deterministic problem, but because of your imperfect information, or rather your inability to evaluate the integrand at all aleph 1 points between 0 and 1, to say that you really know this function is kind of a strong statement. And a statistician walking into the room at this point of the discussion says, well, great, I know how to reason with incomplete information. A numerical analyst has their set of tools, and a statistician has a different set of tools. And the statistician is essentially going to give a probabilistic answer to this question that is, at its heart, deterministic. And so you're phrasing all of your numerical tasks, be they quadrature optimization, even elementary linear algebra problems, as inference problems. And the disadvantage, particularly if you're dealing with, say, an end user who's used to getting one number back, is that from the perspective of that end user, you're actually giving them less now because you're going to give them a fuzzy answer. And what they wanted before was certainty. And probably the computational cost of your probabilistic method is higher than the original deterministic one, so you seem to be paying more and getting less, which is terrible. The advantage, though, is that if you do it right, then you don't pay too much more. And the real advantage is that I'm coming from a background more of uncertainty quantification, where I'm thinking of the problems of quadrature or solving an ODE or a PDE as merely ingredients in some uncertainty quantification pipeline. So I have to solve this PDE, the classic example being Darcy flow minus divergence of kappa grad U equals source term F. U is representing the pressure field in some subsurface medium, in some geological structure. Kappa is the permeability field, which tells me how this rock is made up. If I know what kappa is, I know where the oil is, and that makes me a lot of money. But I want to solve that forward PDE only for the sake of actually figuring out what kappa is from measurements of U and F somewhere. It's not that I know kappa and I want to solve for U. It's that I actually get partial information about U and want to work backwards to kappa. And I just have to do lots and lots of forward PDE solves in order to work backwards to kappa. So very often that inverse problem is going to be posed in a statistical or Bayesian way. If my forward problem has no understanding of probability, I kind of have a European plug and an American or British hole in the wall to plug it into. I'm missing a rather important third prong for my uncertainty quantification pipeline. I want to plug something into a probabilistic procedure like inference for the inverse problem. I should be plugging into it a probabilistic forward problem. So I can, if I adopt the point of view that even my numerical tasks like quadrature, differential equation solves, and so on, are inference problems, then I can fold the uncertainty arising from the solution of the forward problem into the solution of the inverse problem and any other later computations. Some sort of manifestations of this phenomenon: a deterministic solver, say for an ODE, think of the world's worst ODE solver, forward Euler, with an insanely long time step. If you run that on the same vector field with the same initial condition again and again, of course you get the same answer back. That's replicability, that's not accuracy. Right? So I shouldn't confuse replicability of results with their being accurate. So I need some, shall I say, statistical or probabilistic proxy for the fact that my numerical solves have potentially low quality. There are many ways of doing that. Probabilistic numerics is one. I have to do that because if I have even high quality data, but I'm trying to make sense of that using a bad or falsely overconfident model, forward model, or statistician would say a likelihood, then I can end up drawing faulty inferences. And I'll give examples of that on the next couple of slides, and you've already seen some in previous talks. And this is really important because I'm one of those people like George Box who would say that all models are wrong and some are useful. So, and in particular, when we are using differential equations to model physical processes, we know there is unresolved physics. And even in data science and social science, as we move into a large data or big data or whatever the buzzword is era, we're only ever going to see snapshots of a data set. We simply can't inhale an entire huge data set in one go. So all tasks are essentially going to be approximate. So the motivating example that I can't resist giving is quadrature. And this is exactly the example that Percy Diaconis gives in this now quite seminal paper from 1988. So there's well, what can we say about this function, right? You're not going to find this function in your table of integrals anywhere. But I'm guessing everyone here has done a calculus or analysis course, so let's stare at it. What can you even say about this function? Anything you can spot from the formula? Sounds good. Yeah, it's exponential of something.
Positive?
Yeah, we've got positivity, yeah. And that's basically all you can tell. Any guesses as to smoothness?
That's what
Oh. Well, it's smooth, right? And by the chain rule, this is smooth, right? I know. I'm never dividing by 0, so no problems there. That's smooth.
Depending on your step size of quadrature, you can mess things up because you have an exponential of other exponential quantity inside it.
Okay, so that's already leaping ahead to the numerical integration of this integrand. I agree, accuracy of the rule is going to depend a lot on which rule I choose. I'm simply trying to say, at this stage, what do we even know about this integrand? And I can evaluate it very, very quickly at any point in the domain. And yet, already after 2 minutes, we're struggling to say much about this integrand other than smooth, positive, and perhaps with a back of envelope to hand, we could bound it. Would it shock you if I told you it's actually convex? Yeah. Plot it. Even I didn't expect that. I thought that with the cos and the sine in there, this would surely make it wiggly. Actually, it doesn't. It's convex. So there's a lot that we don't know about this function, even though we've successfully written it down using about 20 symbols or less. How does a Bayesian approach this problem? Well, a Bayesian is going to go through the usual steps of a Bayesian statistical procedure of putting, first of all, a prior on the space of integrands, of f's up here. When you evaluate the integrand at one of the integration nodes, to a Bayesian, you're getting data y, which is the evaluation of f at whatever node x. And then you condition your prior given that data, but actually you kind of don't even care about the conditional distribution, the posterior distribution on f. What you really care about is the posterior distribution on the integral of f. We only really care about the image of that posterior under the linear operation of integration, and what with integration being linear, that's going to push through in a very nice way. And this, for a Bayesian statistician, is the one true holy way to estimate the integral, given some prior beliefs about f and the pointwise observations, the standard information, someone in information-based complexity would say, about f. What does your prior represent? Essentially, it's your beliefs about the regularity of the integrand. So if your prior is the Brownian motion prior, so you're saying that you believe that the integrand is continuous but has no more derivatives than that, what you're effectively doing is linear interpolation. Once you see the evaluations of f at the nodes xi, the posterior mean for f is in fact the linear interpolant of the data, modulo some technicalities at endpoints. And the associated quadrature rule is then just the trapezoidal rule that you learn in high school. And for a quadratic loss function, the trapezoidal rule is in fact the optimal estimate of the integral. It's the Bayes rule for this setup. Okay, fine. What would a different prior do? Well, it depends on your choice of prior. If, for example, you use an integrated Brownian motion prior, so you're hypothesizing that the integrand has one derivative but no more than that, then essentially you're doing cubic spline interpolation. So this apparently crazy level of abstraction for posing a simple problem like quadrature as as a Bayesian inference problem, A, it's statistically the right thing to do, but B, it has as its sort of natural point estimators, like posterior means, the objects that classical numerical analysis would be very happy with. But it has dressed them up in probabilistic clothes. And then the natural set of questions to ask is how the statistician's estimate of quality of the estimate, things like posterior variance, and the numerical analyst's preferred bounds, like a worst-case error bound, how are those related? Does the posterior concentrate on the truth, given enough evaluations of the integral at integration nodes, etc.? This is the point where I wish that the videos were working. So this is a second motivating example. So if I integrate the classic Lorenz 63 system, nice smooth ODE, except that it's also chaotic because at the origin there's this separatrix which eventually everything gets close to and then gets sent all over the place. No one can prevent me from choosing to integrate this system using, say, Runge-Kutta. Fourth order Runge-Kutta, fourth order meaning that over a finite time horizon, I incur a global error in solution accuracy of order time step to the fourth. And over each time step, I incur a local error of order time step to the fifth. The standard way of showing this would be what in this video that's not actually showing would be shown as red, and you would see a red dot looping around the Lorenz attractor doing its usual thing. And those would be the marginal plots. The blue would be something that for the moment seems a little bit unmotivated. What I do in blue is I take, at every time step, the usual Runge-Kutta update, and then I choose to perturb that update by a random perturbation of the same size as the truncation error that numerical analysis tells me I'm making. It's sort of a bit backwards, a bit reverse engineered. It's saying, well, numerical analysis tells me that Runge-Kutta's update is accurate to within tau to the fifth, so I shall feel free to change to anything else within tau to the fifth on the grounds that that's a pretty good estimate of the solution after one time step as well. As I say, it's reverse engineering, it's backwards, but that's the reasoning. That turns out to be there's a slight modification to that, but essentially this is what I'm doing. So I'm adding perturbations to the solution at every time step whose standard deviation is, modulo a small technicality, the same order as the local truncation error of Runge-Kutta, and then I rinse and repeat. So I do update, perturb, update, perturb, update, perturb. And I would plot a couple of thousand realizations of that randomized solver in blue, and at this particular time, t equal to 38 seconds, you will see a blue cloud that is quite tightly packed around the usual red point estimator. The reason I plot it for 38 seconds, and I wish I had some more stills, is because in about half a second's time, that cloud is going to get completely ripped in two by the chaotic dynamics of the Lorenz system. It's beautiful, it's a lovely video, I just wish it would work. And the point is that that's t equal to 38 seconds with a time step of 10 to the minus 4, so I've managed to go quite a long time with the probabilistic solver ensemble staying so close to the deterministic solution that it doesn't experience this collapse. Now, classical numerical analysis is just giving me an accumulated error bound of like constant e to the constant times time. This is an ensemble-based measure of the solution accuracy. I choose, the point estimate, red, should no longer be trusted at some point in time. When should it no longer be trusted? When this ensemble explodes. Don't look at the worst case error bound coming from numerical analysis. Instead, just essentially run a number of perturbed solvers, and when the perturbed solvers go crazy, that's when you know that you should have no particular confidence in any one of them. And in particular, you shouldn't have great confidence in the unperturbed solver either, because the accumulated effect of numerical truncation error of locally small order carried along the flow has now become too great, accumulated along the flow, not as a worst case error band. Third example is doing a PDE solve, and in particular doing an inverse problem for a PDE solve. So this is the nonlinear PDE, the Alan-Cahn PDE that Mark Girolami mentioned yesterday. So it's nonlinear because you have this cubic nonlinearity in the solution U up here. It's basically a model for two-phase solids. Imagine a solid that either wants to be, say, north-south aligned or east-west aligned, or has two phases in some sense, and would really like to form sort of coherent globs of phase of either +1 or -1. And we've set things up so that on the unit square, it's forced to have phase +1 on two opposite sides and -1 on the other two sides. And you can sort of see how that's going to make for some interesting dynamics, because if I try and make things +1 here and -1 here, then clearly there's some interest. It would the PD is kind of happy when -1s and +1s cluster, but what on earth is going to happen in the middle? And the parameter theta is basically telling you how much, because it's the parameter sitting in front of the Laplacian, it's the parameter telling you how much this material really doesn't want to have lots of local variation in that phase field U. So we try to infer that parameter theta from observations, noisy observations of a very high quality solution to this Alan-Cahn PDE. So we have a synthetic ground truth that we use to generate our data. But then we try to backwards recover theta, which is 0.04, this vertical spike, using two kinds of solvers for this PDE. One kind of solver being classic deterministic finite elements at various levels of resolution. And what we see is that the coarse solver, so color scheme valid throughout the talk, on the visual spectrum, the stuff at the blue end of the spectrum corresponds to a low quality solver, coarse mesh size or long time step, whatever. Up to the red end of the spectrum means high quality. That's valid for the rest of the talk. So at the blue end, the coarse end, here's my posterior for theta, and you see it changing as I refine the finite element mesh, and something very disturbing is happening. For a coarse solver, I have a very concentrated posterior in the wrong place. So if I didn't have the ability to refine my mesh much further, which is a very practical concern, not for the Alan-Cahn PDE in this toy setting, but say if your PDE is groundwater flow in some subsurface reservoir where the interesting dynamics are on like this kind of scale, but the thing's tens of kilometers across. So you can't possibly resolve down to that fine scale everywhere. The Bayesian alone, with a coarse model, will look at the posterior variance, go, "Ooh, that's nice and small, I'm very happy with that answer." And we'll be very confident in a wrong answer. And then as the PDE solver gets better, naturally the posterior is settling down into the right place, but with a broader posterior variance, which is somewhat counterintuitive. That's not generic, but it is a shortcoming of this particular solution strategy. Solving in a probabilistic way where the solver for U itself returns a probability distribution. In this case, I'm using a Gaussian process, just about the only Gaussian process I'm using in this talk, rather than an ensemble method. At coarse discretization, the blue posterior is here. It's a little bit more accurate than the blue posterior here, but I shouldn't do side-by-side comparison because they're different kinds of discretization. The main point is that the breadth of the posterior for a coarse solver is greater than for a fine solver. In other words, by hook or by crook, I have constructed solvers where the numerical accuracy of the solution scheme is reflected in the posterior width. Yes?
Skeptic might say that, well, it's broad, but it's still not broad enough. So why is it not broad enough?
In this case, I don't know. Okay. I have other examples where the truth is sort of comfortably within the sort of 95% confidence region. The ODE example I'll show later definitely satisfies that. This case it's an improvement, but clearly not the improvement that we would ideally desire. Personally, from an end user point of view, I'll be happy with anything that broadens out the posteriors a bit and prevents end users from falsely attributing excessive confidence to a concentrated posterior. So I would class this one as a partial victory. Okay. So I promised to talk about ODEs a bit more, which is what I'll do. Okay. And also, as Mark pointed out, I'm a card-carrying mathematician, so I kind of have to deliver on that. So I'm basically going to solve either in Rn or, if with an eye perhaps towards evolutionary PDEs in a Hilbert space, a more general state space, the ODE du dt equals f of u with known initial conditions. And I need to build a bit of notation to say what, because being a mathematician, I want to state some theorems. And therefore I need some notation. So this ODE generates a flow, and capital phi will denote the flow map associated to this ODE. In other words, it's the thing that picks up an initial condition and takes it to the induced state at a later time t. Capital phi, true flow. And what I'm interested in doing is building a probabilistic approximation to solutions of this ODE. And being a mathematician, I want to say what the convergence properties of such methods would be. And we're going to follow an ensemble-based approach like in the video that didn't play. And if you really want to see things done purely in terms of Gaussian processes, then I recommend the paper of Mickey Schober and Philip Hennig et al. And I believe Philip was here last year, right? Yeah. Okay, so he's already talked about that. Okay. So if I'm going to prove things about the convergence properties of such sort of randomized integrators, then I need assumptions. And the first set of assumptions is really just about the flow that I'm trying to approximate. So reality itself needs to be reasonable. And reasonable in this case means that the flow map needs to be globally Lipschitz. Actually, we're working on relaxing that at the moment. So that means that if I pick up two initial conditions, confusingly here called U and V, and I hit them with the flow map, then they get spread out by no more than 1 plus some constant times the amount of time that I have run the system for. That's weaker, for example, than what Patrick Conrad and friends assumed in this paper that made Mark grow a huge raggedy beard, because they needed to assume that the vector field was Lipschitz, whereas this is just that the flow is Lipschitz, which, if you know some dynamical system stuff, I assure you is significantly weaker. The second ingredient, so we know something about the exact flow phi. The second ingredient is to say something about the underlying deterministic numerical method. So if I'm integrating, let's say for simplicity that I'm integrating using a fixed time step, then what I'm effectively doing is I've introduced a numerical flow, which I'm going to call psi. So exact flow phi, numerical flow psi, and I'm generating approximate solution. So here's my notation for this section. Little u means the exact solution to the ODE. Big U means a numerical solution. So the exact solution, if I know the solution at time tk, I hit it with the flow map through one time step, and I get out the exact solution at the next time step tk plus 1. On the numerical side, I have a numerical solution. I hit it with the numerical flow, i.e. forward Euler if I'm being stupid, implicit Euler if I'm being slightly less stupid, a symplectic integrator if that's what I have that's appropriate for this particular problem, blah, blah, blah. But I take the previous numerical state, hit it with the numerical flow map, get out the next numerical state. That's how I'm generating my approximations. And so the second kind of assumption that I need, having already assumed something about the exact flow phi, is that I need to know that the numerical flow map is accurate in some sense. Accuracy in this case meaning a uniform bound on the local truncation error of order q plus 1. So the numbers you kind of need to remember, so capital phi is exact flow. Capital psi is the numerical flow. And Q you should be thinking of as accuracy of psi. There's one more number you'll need to remember. So I've got an underlying deterministic method that's accurate to local order Q plus 1, which means global order Q in the time step. How do I noise this up in a somewhat principled way? Okay, if I write down the integral formulation of the ODE, the exact state at some later time t can be got from the exact state at time tk just by integrating f, the vector field, composed with the solution between tk and t. Trouble is that I can't do that integral precisely because I don't already have u in hand. And then Bayesian or probabilist or non-Fisherian comes along and says, oh great, I have a partially understood integrand, let me put down some prior beliefs about what that integrand looks like. So numerical integrators in this philosophy boil down to a choice of model G for f compose U, subject to certain common sense criteria and assumptions about the regularity of the vector field and the solution that you're hunting for. So in the Euler world, what you might do is you might posit a Gaussian random field or a Gaussian process model for that unknown integrand. What that's effectively going to produce for you is a sequence of randomized approximate solutions where, so let's look at the second line first. In discrete time, that's what you would do deterministically. The new state is old state plus time step times vector field evaluation. In the new world, what you're doing is you're perturbing that with the final state, the Gaussian distributed final state of your Gaussian process psi, which is really your standard numerical integrator, G minus your standard numerical integrator. So you're folding the mean of the Gaussian process into the psi map, the numerical flow, in this case forward Euler, and then you're using the leftover, the residual part, to model the local truncation error. A numerical analyst at this point starts hopping up and down and saying truncation errors are A, not centered, and B, not Gaussian. The not centered part, I'll admit, we need to extend our analysis to cope with the non-centeredness part, so folding in systematic error. The Gaussian part is going to turn out not to be such a bad mistake to have made, but hold on for the moment. Another bonus of doing this is, if you like this thing, is you have what numerical analysis is called continuous output. So you may have, for example, a solution to your ODE here at this point in time, your next time step is over here, and then along comes someone with a data point that requires you to understand the solution here in between. Continuous output means that you have a principled way to say what the numerical solution would be at that intermediate time point, and that pops out from having a continuous time Gaussian process. So more generally, what you're doing is you're taking your black box numerical integrator and perturbing it with something that really it's reflecting your prior beliefs about the structure of the local truncation error of that black box numerical integrator, which means it's really a statement about your beliefs about the regularity of the vector field f and the solution of the ODE in that vector field F in terms of how many derivatives should this thing have, which when you think about it is not too far from making an assumption about the order of the numerical integrator you're using, because a lot of these numerical integrators are constructed by looking at a Taylor expansion of the vector field, and of course that Taylor expansion has to stop once you have no more derivatives in hand. So that in a nutshell is what we are doing. We are using Gaussian processes independently on each time interval to perturb or inflate the predictions of a standard numerical integrator in a way that is going to be, but isn't yet, reflective of local truncation error. And then it gets carried on along the flow. And I should say at this point that this is purely intended to model the subgrid effects, to model the stuff that is not resolved in between the partition points on your time grid. There's also a fascinating wealth of work on the accumulated effect of floating point and round-off error. I'm assuming real arithmetic here. So even if I do numerical analysis in real arithmetic, I still incur errors, and that's what I'm trying to understand here. If you want to look at the effect of accumulated round-off error, there's a couple of references there. Also great work by Ivo Babushka and many, many others. So the third assumption that I need in order to state and prove anything about these randomized integrators is something about the scale of the noise that I'm adding. And so that's my fourth magic number, is that P is the size of the noise. So expect a second moment of psi is big O of time step to the 2p plus 1. And if I don't quantify my assumptions, then I can't get anywhere. But these are the essential things that you've got to remember. Phi is the exact flow, psi is the numerical flow. Q is just a number telling you how accurate the numerical flow is in the numerical analyst standard sense, and P is something that's telling you how large the noise is. And if you're thinking that I've got one too many things here and that P should obviously be Q, then you're on exactly the right track. Okay? So the prime example here is that you might model this truncation error as an integrated Brownian motion. So essentially, you're assuming that you've got one derivative in your local truncation error, but no more than that. And in that case, then that's the scaling you should be using there. And I'm going to sort of drop the Gaussian assumption now, because it will turn out, for the result that I'm about to state, that I don't need to be assuming that my truncation errors should be modeled on a Gaussian process. Anything with this error bound highlighted in red will yield exactly the same limiting result as time step goes to 0. So in some sense, the role for numerical analysts here is to come in and give us better priors for truncation error that are, realistic and informative at the time step positive level. They're not going to change the limiting theorem, the convergence theorem as time step goes to 0, but what they will do is give us more quantitatively accurate and realistic and respectable predictions at finite time step. So, pretty much ready to state a convergence result here. This is what you would learn in Numerical Analysis 101, that over a finite time horizon, the maximum difference between the exact solution to the ODE and the numerical solution to the ODE is of order some constant times time step to the Q, because that's what having global order Q means. Right? Let me just dress this up completely unnecessarily and just put 2's everywhere. There's a reason. Okay, so this is the same thing as I said before, just I have squared everything inside. The reason I do that is because for the randomized integrator, I'm going to state something about the convergence of that integrator in mean square. So there are going to be squares everywhere. Namely that the mean square error maxed over time is, well, the 2q doesn't surprise you, because that's the error that you had before, but it's minned with the size of the noise that you are adding. In other words, you can tolerate, your numerical integrator can tolerate being noised up with additive perturbations up to and including the same order as the original truncation error, and you keep the same convergence rate in mean square. So a natural choice is the one that I just alluded to, of take p equal to q. That your scaling for the noise should be your beliefs about the regularity of the solution that you're hunting for. And if you add larger noise than that, then you start wrecking the convergence rate you started with. So you inherit the 2q that you got from the deterministic world. You just have to min it with the scale of the noise that you had before. This was, in the Gaussian world, the result that Patrick Conrad and friends proved in the paper that called The Beard. It can be improved if you care about such things. Notice here I've got time supremum, time max outside the expectation. We can improve that and drop the Gaussian assumption and bring the time supremum inside the expectation and keep the same rate. The constant, of course, will change because you're invoking clever machinery like Burkholder-Davis-Gundy inequalities and other stochastic analysis tools. But it's the same message that the deterministic convergence rate will not be wrecked by adding noise that is reflective of the truncation error of the numerical scheme you're using. So now you actually have convergence not just for each time individually, but in the space of paths. You can also drop some further regularity assumptions like making things locally Lipschitz instead of globally Lipschitz. Han is doing great work checking the details on that. But in view of the time, I think I should just give you a view of the inverse problem world. And then, well, judging by yesterday, the lunch may not be here. But no lunch, OK. No lunch, more mathematics. Right. Anyway. Let's do an inverse problems example, in which we'll actually get the point that you alluded to of having a posterior that really does what we want in this example. So this is a nonlinear oscillator. It's an ODE in just two variables, u1 and u2, that evolve according to those two components of that vector field, with three parameters in there: θ1, θ2, θ3, and this, because of that cubic nonlinearity up there, is exactly one of the things that we wanted the strengthened convergence theorem and the relaxed regularity assumptions for, because this thing is not Lipschitz. It's got this cubic nonlinearity at infinity. Fortunately, it's inward pointing, so life is nice. And what we're going to do is we're going to see noisy observations of the, let's call it exact, but really it's a high-quality, fine time step solution to this ODE at integer times, up to time equal to 40. And then we're going to try to recover the governing parameters θ1, θ2, θ3 from those noisy observations using an absolutely awful integrator, explicit Euler, which no one should ever use, but that's exactly what you do. You set up a straw man and knock it down. So explicit Euler is second order locally, first order globally. So that means that we're in the world of q equals 1, and the convergence theorem tells us that then a sensible choice is p equal to q equal to 1. And so I'm going to add noise to the explicit Euler solvers, either no noise at all, which corresponds to scale factor sigma equal to 0, or I'm going to compare that with sigma equal to 0.2. And yes, a thing we should absolutely be doing is not just having a scale factor here, but a proper covariance matrix. And even better, we should be learning that covariance matrix on the fly from the data, from the solution that we observe. And that's current ongoing work with Philip Hennig and with his graduate student Hans Kersting. Right. But in this sort of narrow special case, we're going to try to infer for theta given noisy observations of the quote-unquote exact solution. And the exact values for theta are 0.2, 0.2, and 3, and I hope that that will be visible on the next plots. So those are your posteriors for the three components of theta using explicit Euler with no noise. So you see this phenomenon of the posterior width being essentially constant as a function of time step. Purple, remember, the purple end of the spectrum is coarse time step. The red end of the spectrum is a fine time step. And essentially, regardless of the level of time step I choose, I have the same width of posterior. So from a statistician's point of view, I have the same confidence in my prediction regardless of the accuracy of the integrator that I use, which is slightly disturbing. What I do see is that the mean gets corrected as the time step goes to 0, which is reassuring. Numerical analysts would say, well, you should be just looking at the convergence of the posterior means or the map estimators, and that's what you should be looking at, but maybe you can't go that fine. When I noise things up, my posteriors get smushed out all over the place, and importantly, this is exactly the situation you want, that for the terrible time step of 0.1, my posterior is appropriately uninformative. It's smushed out all over the place. Your non-mathematical manager can already interpret that posterior as saying absolutely nothing, and the truth is well inside the support of the posterior. And yet, as time step goes to 0, so as purple tends to red, you see concentration of the posterior on the truth, as you would expect, because after all, the convergence theorem saying that the solutions, the Pn solutions to the ODE are converging to the true solution, that leads you to expect that the posteriors should converge as time step goes to 0 to the truth. There's lots of wiggly, bumpy structure to these posteriors that's totally a numerical artifact. So I guess I should remark on how you do inference for these two. So here the deterministic world is probably one that you more or less understand, that I need to infer for theta given the data y, which is observations of the true solution, or noisy observations of the true solution. So I just build my likelihood for theta given y. I've got my prior on theta, which in this case is log normal, and then I hit it with the usual hammer, which is MCMC. Here I've got an extra parameter, which is the size. Essentially, the xi's are what govern the deviation of the randomized ODE solves from the standard ones. So what I've really got here coming out of the board is a xi axis. And for each fixed xi, so if you think of ahead of time, knowing how many time steps you'll do, imagine pre-generating a list of xi perturbations that you will use for each time step. I can now freeze that. I can run MCMC on this xi slice to get a posterior for theta conditional upon the data y and on xi, and then I average with respect to xi's. So the lumpiness you're seeing here is simply because I have got, I think, about 16, maybe 32 different values of xi, over each of which I've done MCMC, and then splotted it down there. And because each of the individual posteriors is about that wide, for each xi, the posterior sitting out here in the middle of the room is about that wide. And then I'm basically summing about 32 of those to get that kind of blobby thing there. So I'm marginalizing over xi. Next steps. How are we doing for time and for lunch?
Yeah, I think we have like 5 more minutes.
Okay, right. So I'll definitely do this, and maybe I'll then just sort of vamp for a little bit about PDE until sandwiches appear. So things that need to be done. we're in the middle of relaxing the regularity assumptions that are necessary to know about convergence of the randomized forward solver to the truth, and also looking at the impact of having a randomized solver, i.e. a randomized likelihood, on the posteriors. So, and you would like to know that the posterior with this randomized likelihood is in some sense not too far from the posterior with the true solution, the true ODE solver, sort of God's ODE solver, if you could have that, the one that actually solves the ODE to infinite accuracy. It turns out to be a little bit tricky to get convergence rates if you only know that the flow is locally Lipschitz. So actually I kind of skipped over that. So if I only have the flow and the integrator are sort of locally accurate, you know, they're globally Lipschitz on each bounded compact ball in space, but then the Lipschitz constant might be blowing up as I expand that ball, that domain, to infinity. Then I can show convergence of the method, but I only know that that the error converges to 0 as time step goes to 0. I don't have a rate anymore. So this is a situation that's very familiar in the study of stochastic differential equations, where we are adding noise that is at a much smaller scale than the Brownian scale that stochastic analysis works at. But nonetheless, we're encountering the same problem, that if you only know that the flow is locally Lipschitz, then that's convergence of the exact of the numerical solution to the exact one could kind of be as slow as you like. So one of the things we have to do, and we're working on, is controlling the relationship between the blow up of the Lipschitzness of the vector field, not of the vector field, of the flow, linking the growth rates of those two constants to try and get a rate back for the convergence theorem. Another big thing, and we were talking about this just the other day, is that it would be nice to have probabilistic numerical integrators that respect known structure in the ODE or in the problem. So a good example is, suppose that I am solving an ODE that corresponds to Hamiltonian dynamics, conservative dynamics. So the total energy, kinetic plus potential, in that system must be conserved. One of the ways that, if you're teaching numerical analysis, you show students that explicit Euler is terrible as an integrator is that you do the simple harmonic oscillator and you show that the energy blows up, the trajectories spiral off to plus infinity. And then you show that implicit Euler is only mildly better because instead that one damps and energy dies and the trajectories go into the middle. And then if you're very smart, you say, but it's not so bad. We can construct integrators that will exactly preserve, if not the original total energy, then a discretized, slightly perturbed version of the total energy. And if you're going to be running your integrator for a long time, that's a really important stability condition to have, this preservation of energy, that trajectories will not die off to zero energy or explode. And now if we're going to perturb or noise up integrators like that, the last thing we want to do is wreck the conservation of energy that has been so carefully incorporated into existing deterministic numerical methods. So a challenge there is to come up with perturbations that keep you on your energy contours or preserve other first integrals of that dynamical system. In the case of linear stuff, we kind of know how to condition Gaussians on linear information because, you know, Gaussian linearly conditioned is another Gaussian. Gaussian non-linearly conditioned, oh God, I have no hope. But, well, I have hope, but I'm going to have to be smart now. So that's another open question. And the other one is something that I alluded to just now, that what we want to do is to, in a sort of an on-the-fly or adaptive way, learn what the covariance structure of the noise should be. So numerical analysts will tell us that Gaussian is not a good model for local truncation error, and we'll partially pacify them by saying it doesn't make any difference as time step goes to 0. But please help us design better ones for finite time step, by all means. but then there's also the thing of, I've really only used things where here I've got an uncontrolled constant in my estimate, my assumed estimate on the size of the noise that I'm adding. What I should really do is make that a known matrix or a known operator, because who says that I'm making the same kind of truncation errors in all directions in state space? And this is where, again, we would expect to connect with classical numerical analysis, because they have great ways of doing a posteriori error estimation, so that you take a step, you compare with, say, the predictions of a higher order method or the same method with an intermediate time step, and that gives you a very good local idea of how wrong your numerical predictions are. This is then typically used to decide whether to refine the time step. But I'm deliberately tying my hands behind my back and saying, I don't want to refine the time step too much because I'm worried about computational cost. Instead, I'm interested in appropriately noising up my predictions at a fixed time step. What I would like to do then is use those a posteriori error estimates to tell me what the constant in front of, or the matrix in front of time step to the 2q plus 1 should be. So I think I will skip the PDE, especially seeing as Mark talked about it, and just give my closing remarks again. And if the sandwiches are here, great, but if not, it's getting kind of hot. So what's our sort of mission statement again for probabilistic numerics? Whether done in a Gaussian process way or in a pathwise ensemble way, this is, to me, more of an implementation rather than philosophical point. The philosophy that we are adopting is that we want to fold the uncertainty arising from numerical errors such as truncation and discretization into even the forward solve of a deterministic problem, so that it's ready and waiting in probabilistic form for the inference procedures that we already know and love and are ideally waiting for probabilistic information like Bayesian inference, so that you can propagate that uncertainty properly into later computations. And we want to do these probabilistic representations to be somehow more reflective of reality than sort of the usual numerical analyst's error estimate. You know, you might take the standard numerical analysis error estimate and simply basically use that as the scale on your likelihood, on your misfit term. But that's going to be a very conservative way of doing it because of the way that most numerical analysis error bounds blow up exponentially. They're usually of the form constant e to the some other constant times time. That's going to really inflate your observational noise unnecessarily, or should I say perhaps your solution noise unnecessarily quickly. Whereas if you look to carry your numerical errors along the flow in the style of, say, that video that would not play, where I was just going to carry an ensemble along the flow and it blows up when it blows up, that's a more realistically conservative way of propagating your numerical errors. The win here is that we then don't confuse replicability of deterministic simulations with their accuracy. We definitely know what we're doing in the Gaussian world, and we can start to see how to go beyond the Gaussian world for ODEs, but for PDEs we are still somewhat lacking in tools. In response to one of the questions that came yesterday, someone asked, this is all very well and good for linear PDEs, what about for nonlinear? And the example is that Alan-Cahn equation that I showed. That's nice because it decomposes as linear plus invertible monotone. And so we can just about get away with pulling a Gaussian process trick on such an object. But for a general nonlinear PDE, I still don't know what we should do. And we could definitely do with designing better priors simply because the numerical analysts won't listen to us until we do. So going beyond the Gaussian world is essential. And we need expertise at this interface of numerical analysis, where we need to build the right kind of, well, first of all, we need to convince the numerical analysts to think probabilistically. And second, we need their help to build a good prior. And then on the other hand, we're, as always, looking at exploring, hopefully in a tractable and computationally efficient way these new posteriors over solution space and exploring them quickly so that we can propagate the posterior over ODE or PDE solutions through a later inference block when we have to do parameter inference. Mark already talked about probabilisticnumerics.org or probnum.org, where you can find everything from the prehistory of this kind of line of thought to more recent contributions, such as our own, but also those of the Tübingen gang and Mike Osborne in Oxford, et cetera, et cetera. And if you feel like playing with any of the code, then that can be found openly on GitHub on John Cocaine's account right there. And with that, I shall thank you for your attention.
Okay, well, while lunch is being set up, we'll have some questions, so thank you very much.
Thank you.
Questions?
Let's say you try to make things more skeptical slightly, and say instead of having a Gaussian trial, you make a student T trial. And why I say that is because you can reuse all of the GP machinery which you have well developed, the whole theory about kernels, and extend it to student T processes. Do you think that might help in this whole probabilistic numerics?
Yes and no. I wouldn't go about replacing everything with a student T for the simple reason that numerical analysts are already quite rightly objecting to the idea of having a prior for truncation error that has unbounded support. So if anything, we need priors that have compact support. On the other hand, there are plenty of knobs to turn in a PN setup that do call for a heavy-tailed prior assumption, things like priors on regularity. So if I don't know ahead of time how much regularity I should assume on my ODE or PDE solutions, then the natural thing to do is to put some kind of prior on regularity and do a hierarchical inference. And in that situation, I personally would put a heavy-tailed prior on regularity structures or on variance structures to keep the procedure appropriately open-minded there.
One thing I was going to ask is, in your results, you had, when you're using a bad solver in a deterministic way, you had very constrained posteriors.
Mm-hmm.
And we've noticed the same thing in where we've got a structural error. So we know the model is wrong for the data.
Yep.
We notice the wronger it is, sometimes the more confident you are. Do you have any feeling for why that happens?
Well, there is of course a structural error in the example, say, of the explicit Euler trying to make sense of Fitzhugh-Nagumo. The structural error there is that forward Euler has a systematic time shift off the true dynamics. So in some sense, it's trying to, when you look at its posteriors for theta, it is saying, well, because its dynamics are, I'm running low on blood sugar, so it's either its dynamics are too slow or too fast, and it's sort of correcting for that by changing the thetas, which are essentially timescale parameters. So that's one reason why it's making this systematic error. I think it's going to be on a case-by-case basis. So that explains the shift in the posterior mean, but the posterior variance, I think, is essentially because replicability says you're seeing the data at too high a precision. I think there are other fixes, and you could try to use the numerical analysts, if not global error bound, then a posteriori error bound, and use that as the norm. You know, when you do your log likelihood as something like 1/2 norm y minus observation operator applied to u, you've got some norm there, gamma. Well, that gamma should really depend upon the time step, and I think an alternative approach would be to shove the a posteriori error estimate as a multiplier in there. I would be interested to see if that boils down to being equivalent to perturbing the solution. I don't think so, but I think it's worth checking.
Everyone's clearly got their mind on lunch.
quite rightly so.
Okay, so let's thank Tim again.
Thank you.
That was very interesting.
Thank you.
One other thing I was going to ask about the perturb solution.